Hey, how's everyone? Who's sleeping? Will you raise your hand if you're sleeping? I don't know. Who's not sleeping? Yay! So, hello everybody. Thank you for being here for my talk today. My name is Henri. I work at the Starknet Foundation where I'm VP Product. And today I will talk about ZK proofs as primitives. Primitives for blockchain developers and primitives for smart contract developers in particular. So during my presentation, I will go through what is here on the slide. So I will start with a small explainer, a refresher, if you will, of what proving is, how it is used today, right? Then I will explain how proving can be used by smart contract developers to come up with more interesting systems, more interesting protocols, and more interesting smart contracts. And then I'll explore a couple of use cases that can be useful, that have a potential of being somewhat interesting, and you'll tell me what you think. So I'll start with a short explainer of proofs, right? Who here feels comfortable with what zero-knowledge proofs or validity proofs are? Okay, who feels somewhat confident? I've heard about it, I know a little bit about it, but not too much. Okay, who has heard about proofs but has no idea how they work, but they're a nice word, proofs. Come on, 5 letters, proofs. Okay, so people are fairly technical, you know what proofs are. So proving is a mathematical tool that enables a person, which we usually call the prover, to execute a program and prove to another person, who's called Bob, as often in crypto, and who's called the verifier also. And Alice gets to prove to Bob that she performed a specific computation without having to reveal to Bob what went into doing that computation, but also, importantly, without Bob having to do the computation himself. So it saves work on Bob, and it preserves information on the side of Alice. ZK proofs are a fundamental mathematical breakthrough. They're not specific to blockchains. They're mostly used in blockchains today, but they have a field of application that is much wider. So proving today is mostly used in prods in blockchain networks that are called ZK rollups. In a nutshell, a lot of blockchains today are faced with a scalability dilemma, right? Either so if they want their network to be decentralized, they need every participant to replay everything that is happening on the network, right? Blockchains are often called distributed ledger, when in reality they're not distributed, they're replicated. And so most networks have to find a balance between enabling enough people to participate in the network and having a lot of throughput. And ZK rollups enable to have sort of the best of both worlds, because you can have more performant machines that operate the network and then generate a proof that they did so correctly. And now the participants in the network don't have to operate the network. They can just verify the proof that the network was indeed operated properly. To a degree, ZK proofs in ZK rollup enable to do to execution what mining and proof of work enables to do for security on proof of work networks, right? And so in ZK rollup, this is where most of what is being done today is done. I have a small lexicon for people who are a bit lost, who knows. So as a lot of things in crypto, also we're terrible at naming things, so we use the same name to distinguish between several entities. So the first I want to define is the prover software. A prover software is a computer software that you run on your machine. It allows you to run a computation and generate a proof that you did so properly. Then there is the prover, the entity, and here the prover is the person who runs the prover, right? So think of it, if you think about an Ethereum node, that is the difference between a node and a node operator. Here you have the prover, the software, and the prover operator, the entity, but it's often called the prover. And we have the same distinction for the verifier. The verifier is the software that takes the output of the prover and then will give you, yes, this is a correct proof, or no, this is an incorrect proof. And so you have a software that is called the verifier. Interestingly, that verifier can be a smart contract. So you can write an Ethereum smart contract in Solidity that verifies ZK proofs. Then you have another entity, which is a software, an entity this time, which is a verifier that runs the verifier. It can be a person, it can be a machine, it can be a smart contract. It will eventually also be agents. And then finally, for ZK rollups, you have another entity which is called the sequencer. The sequencer is the entity that runs a big machine, aggregates transactions, batches them in a block, and then gets into a relationship with the prover to prove that those blocks are correct. In a nutshell, that's how ZK rollups work. So far, so good? Yes, I see thumbs up. Nice. All right, so now I want to talk a little bit about ZK proofs as primitives for smart contract, or ZK proofs as primitives. So the first thing that is important to understand and to note is that at this stage, most of proving in production is facing a trade-off. Writing a prover software is actually really difficult. It's not super common, right? So they're fairly specific programs. You will write a prover for a specific application, or you will have some provers that are general purpose. But the provers who are general purpose are in general harder to operate, and so you see mostly specialized actors using them. So you sort of have this dichotomy. If proving is done by smaller entity, then designing the prover is difficult, and you don't have many systems doing this. And if proving is general purpose, it will be mostly done by specialized entity that runs ZK rollup, right? So you see mostly this dichotomy, ZK rollups who are operating provers at scale, and then in specialized applications, you will have smaller provers and verifier, but the applications are fairly narrow. They're not extremely complex. They don't allow for general computation. It is a little bit the same, you can use the same mental model where we are today as what computing would be in the 70s. I know it's not a perfect comparison, but bear with me. In the 70s, you could use computers at scale. You would have those big mainframes that would operate things for a lot of people, but it was not very common for people to have their own machine. It wasn't very common for people to run their own server. And if you had people doing some sort of compute on their own server or some smaller entities running their own servers, those servers would be, specialized circuits or specialized machines. They wouldn't be general purpose. Now, protocol level proofs, as we see them, aim to flip that and enable a democratization of proving. They enable using the same prover for general computation, but at a level that is not for a big operator to run, but for smaller operator to run, maybe even individuals, right? So it's a little bit like informatics and personal computing in the 90s. You went from having a system with very big machines and very big operators to a system where there were a lot of smaller machines that in the beginning couldn't interact with each other, but eventually made it there, right? So why is this interesting? Proving in general is a really powerful primitive. You get to play with it for a bunch of different directions that I'm going to get into in a second. But the general gist of what this is we want to make proving a primitive that smart contract devs can use easily, very easily, to delegate part of their smart contracts to the outside for scalability purposes or for privacy purposes. So what does easy mean? It means that when you want to write a smart contract that leverages a proof, one, you don't have to learn a new language. You can use the same language as the one you're writing your smart contract in. Two, you can reason about your programming environment in the same way that you reason about your programming environment when you're writing a smart contract. So the concept of a transaction still is there. The concept of a block still is there. The concept of interacting with another smart contract is there. Same for account and state. So you get to write smart contracts that have proofs that affect their state, and the same code that you can run on a public blockchain, you can also prove outside. And that's a very powerful primitive, though very unexplored. So this is not just words. I have a small demo up, so please flash it. Kudos to Adrien who has worked on this over the past week to make it happen. This is something that is coming to production on Starknet in a couple of weeks, and you can already try it today on testnet. So this is not a fully fledged system, of course. It's a first version. We're developing it right now and we're rolling it out to see how people interact with it, to see what people will start building with it, and to see what interesting use cases may come out of it. Things that will come in the future will include having a much bigger proof size, so being able to prove much larger workloads from outside of your smart contract. Will also enable more usage of advanced functionalities inside your proofs. You'll have full recursive verification. I'm not going to go into recursion now because I'm not going to go into recursion now. And then you can do transaction aggregation, hopefully sometimes in the future. All right, so now let's look at potential use cases, right? What can you build with this exactly? So one thing, of course, you can do stuff on the side of privacy. Privacy is the original use case that got people in crypto excited about ZK proofs, right? The first time ZK proofs started getting traction and interest in the crypto space was applied to privacy. And then eventually people started thinking, oh, actually, we can use them for scalability, which is what ZK rollups are. But that first initial instinct, yes, we can use this for privacy, this was right. And people are coming back to this, and we're seeing a lot more innovation. However, innovation in privacy is hard. It's hard for several reasons. One is that it's a very unexplored use case, and it's really hard to reason about, right? Thinking how to do a private app can mean 1,000 different things to different people, so it's really hard to reason about. But it's also really hard to build privacy applications. One of the reasons for that is that privacy applications tend to be very compute heavy. They ask a lot of resources from the place you execute them, right? So the infrastructure wasn't there a few years ago. Now it's getting there, and now with proofs, you can generate even more stuff outside the chain. So making proving easier enables for a lot of experimentation around privacy, both on the side of new protocols, new cryptography that you can bring to smart contracts, but also in the realms of more interactions. What do you hide? Where do you hide it? Why do you hide it? Who do you hide it from? How do you enable people to prove that they did something without disclosing it? All of these are, like, it's not one spectrum, it's a set of parameters that define privacy application, and making it easier to use will lead to a big leap in innovation in the privacy field. One thing that Starkware and Starknet Foundation are currently working on is Stark 20. So Stark 20 is a privacy protocol that we announced, I don't know, a couple of weeks ago, something like this, and we released a white paper soon after. And it's a privacy protocol that essentially enables you, as a depositor of any ERC20 on Starknet, to deposit this in a smart contract and generate a proof that you did that deposit. And later on, you can use that proof to transfer assets from within the pool. The cool thing is when you're using that proof to transfer assets within the pool, you don't disclose when you deposited those. And that's a key change with how public blockchains usually work. If you deposit $1 in Aave and later you move it elsewhere, it is very easy to link when you deposited it, and it is also linked to your account, right? With this construct, you can deposit in the pool and then later on move your funds elsewhere without disclosing who you are or without disclosing how much you're moving. You're able to split deposits, collapse deposits, and then eventually you're also able to move out of the pool. What is cool with this is that the proofs that you're using are all protocol level proofs. They're all using the same smart contract language that is used in the pool, which is Cairo. They're using the same toolkit. They're very easy to reason about. They're very easy to audit. And as a result, the contract is also easier to integrate and interoperate with existing DeFi applications on Starknet. So your privacy application doesn't have to be entirely siloed. You can enable stuff like private DeFi, depositing in a DeFi protocol, and then shielding the deposits and making those deposits shielded. And you can enable also some flavor of private swaps. You're in the pool, just jump out, swap your asset, jump back in, and a ton of other use cases. We're making the privacy pool composable. And one of the first use cases we're going to use this privacy pool on is Stark BTC. Stark BTC is a Bitcoin wrapper that is going to launch on Starknet. It will be in the beginning operated as a federation of signer, and it will eventually move to a more secure protocol of signing, which is BitVM, which will be 1 of M instead of N of M, and eventually, hopefully, we'll move to a more trustless setup. But the key thing about Stark BTC is that it will have shielding from the get-go. You will be able to go from Bitcoin to Starknet and shield your assets very easily, and so you'll get some flavor of private Bitcoin, which is exciting. It's something that is hard to do on Bitcoin, and you'll get to do it through Starknet. All right, so that's one thing you can do with privacy. Another thing you can do with protocol-level proofs is another flavor of scaling. So I talked a little bit about Zico rollups in the past, and I want to talk to you about something that is a bit more niche, which is called, or we call them, ephemeral rollups, right? So I'm just going to check the time. All right. So ephemeral rollups are this construct where, for some use cases, think ticketing, live event payments, competitive gaming, having latency or having congestion on a network is a really bad thing, because if you have 100,000 people who are waiting to buy their beer at a festival and the transaction just doesn't go through, you're going to have a bad time. You're going to lose money because you can't charge them, but also people get angry. So you need very high SLAs. This means that for this kind of use cases, payment processors actually have servers on premises processing those transactions. And they can't use the blockchain for that because they can't afford delays. Sometimes they don't have internet connection. With ephemeral rollup, you get to process all of those transactions off-chain, batch them, and then settle them later on-chain. This can be done for payments, for ticketing, and for gaming. So yeah, it's ephemeral rollups. They're localized in time. They're not a chain you need to set up and then maintain forever. They can live for a weekend or a couple of weeks. And they can be localized in space. They can be off-grid and then settled on-chain later on. And they're composable with host chains. You don't need people to set everything up to deploy a new wallet, move to a new rollup. It can be interoperable with the chain they're already on. And in particular for events, it means that it's easier to maintain composability. So that's for scale. I'm going to move a bit quickly on this one, but I want to mention one potential application of private proofs, which is of proofs at the protocol level, which is private DeFi. So private DeFi is very unexplored, but I want to propose a thought experiment. If a smart contract is able to verify a proof, then it means that that smart contract can have a private state. So you can have private smart contracts. These smart contracts can do a bunch of stuff for you, like smart contracts do. So what does that mean, right? What exactly does it have? It can have private inputs. You don't have to display what it is you're putting in the smart contract to execute it. And it can have private logic, meaning people who are watching the chain don't know what this smart contract is doing. One use case for this is, for example, private peer-to-peer lending. So Renault, who is there, will post 1 Bitcoin, and I will post $50,000 in the smart contract. Renault will then draw from this credit line and be able to borrow it. We agree in advance on an APY, we agree on a liquidation threshold, we agree on an oracle, and none of that information lives on chain. Nobody can see it. The benefit to Renault is that he can negotiate with several loan providers, and nobody will tell him, oh, but you're giving Henri a really good loan because you like him. Why don't you like me and give me a really good loan? Right? Because nobody can see the parameters. Nobody will be able to hunt his position down to try and close him and steal his and get his collateral. So that's a benefit to him. And then if you combine this with the privacy pool I mentioned earlier, now you can get to something that is really interesting where you can really get cooking. You can have a smart contract that receives private nodes. Nobody knows how much is posted. Maybe Renault posted 1 BTC, maybe he posted 100. Who knows? Nobody knows, aside for Renault and myself. And all of the conditions, all of the liquidation also is done quickly. So anyway, is that useful? We'll see. Come and build it, see if it's is valid. One interesting thing that I'll leave you with is that this behavior already exists with OTC Lending Desk. This could enable a private and non-custodian version of this. Summing up, protocol proofs are cool. You get to build a ton of new stuff, a ton of new smart contracts. Up until now, proving was difficult. It's getting much better. And if I said something too stupid, come talk to me later on, explain me why it's stupid, and then let's find a way to make something not stupid with this together. Thank you.